Einstein's theory of relativity transformed our understanding of physics and the universe. In this video, we'll explore two key concepts: time dilation and length contraction. First, let's talk about time dilation. Einstein showed that time isn't constant. It changes with speed and gravity. Imagine Tom is on a fast-moving train. A beam of light shines upward from the floor and is reflected back by a mirror on the ceiling, taking time t0 to complete the round trip. From the side of the road, however, you observe the light taking a longer path due to the train's motion. Since distance equals speed times time and the speed of light is constant, this longer path means that time is passing more slowly for Tom than for you. In other words, Tom's time is dilated. You might wonder, could time slowing down extend human lifespan? The reality may surprise you. Time dilation only occurs between different frames of reference. From the roadside, you'd see people on the train moving slower. But for those on the train, life feels normal. In fact, they would see the world outside in slow motion. So, they won't feel like their lifespan is extended. Besides speed, gravity also affects time. Einstein's general relativity describes gravity not as a force, like Newton did, but as a curvature of space-time caused by mass and energy. This curvature not only affects how objects move, but also how time flows. In stronger gravitational fields, clocks tick more slowly than in weaker ones. Imagine two twins. Alice stays on Earth, and Bob spends time near a massive object like a black hole or neutron star. Both start with synchronized clocks. After Bob returns to Earth years later, Alice will have aged much more than Bob thanks to time dilation. In 1971, Einstein's prediction of time dilation was confirmed by physicist Joseph Hafele and astronomer Richard Keating. They flew 4 cesium atomic clocks on commercial planes, traveling in both eastward and westward directions. This was done to test time dilation due to speed, as predicted by special relativity, and time dilation due to gravity, as described in general relativity. After the flights, they compared the clocks with stationary ones on the ground. Since the planes were at a higher altitude, they experienced weaker gravity compared to the ground, where the gravitational pull was stronger. This caused the clocks on the ground to run slower due to gravitational time dilation. Conversely, time dilation caused by the plane's speed made time on the plane run slower. Therefore, on the eastward flight, the clocks lost time due to the higher speed. On the westward flight, the clocks gained time because the plane was flying slower relative to Earth's rotation. The lower speed made gravitational time dilation more noticeable. The experimental results showed that after the eastward flight, the airborne clocks had lost about 59 nanoseconds, while after the westward flight, the clocks had gained about 273 nanoseconds. These results closely match the predictions made using Einstein's theories of special and general relativity. After understanding time dilation, it's easier to grasp length contraction. Imagine Tom speeding past you on a train. The length of the train is the distance it travels from point A to point B. For Tom, the train's length L0 is determined by its speed v, and the time he experiences t0. For you, the length L1 is determined by v and the time t1 that you observe. Because of time dilation, t0 is shorter than t1, which means L0 must also be shorter than L1. So you perceive the train's length as shortened. However, from Tom's perspective, it's the scenery outside that appears shortened.